Welcome to Math 1342, Elementary Statistics. This lecture is on Chapter 3.3, Measures of Position. As always, I include the objectives here. You can write them down to make sure that you have notes or collect the information. I also list this at the end to make sure you feel like you've covered the material. So the first thing we're going to talk about is something called a z-score. So what if we asked a question, who is taller, a man 73 inches or a woman 68 inches? The obvious answer is that the man is taller. However, men are taller than women on the average. Suppose the question is asked a different way. Who is taller relative to their gender? A man 73 inches tall or a woman 68 inches tall? One way to answer this question is with a z-score. So let x be a value from a population with mean mu and a standard deviation of sigma. The z-score for x is calculated this way. We take the data point x, subtract the average, the mean, and then divide it by the standard deviation. Z equals x minus mu over sigma. And what this z-score tells us is how many standard deviations that value, that x value, is from its population mean. A value of one standard deviation above the mean, meaning it's to the right of the mean, this would have a score of +1. And a value 2 standard deviations below the mean, on a graph this would be to the left of the mean, this z-score would be -2. So let's look at this. A National Center for Health Statistics study states that the mean height for adult men in the U.S. is 69.4, or mu equals 69.4, and the standard deviation is 3.1 inches. For adult women, the mean is 63.8, mu equals 63.8, and sigma, or the standard deviation, is 2.8. So now we can use these actual data measures, 73 for men, 68 for women, to figure out who is taller relative to their gender. Because the further they are away from the average, the further the greater they are, the difference between their gender. So here we're just plugging in the values. The data point 73 minus the mean divided by the standard deviation, and we see that the man is 1.16 standard deviations away from the mean. So he is a little bit over 1 standard deviation above the average to the right. When we do the same thing for the woman's height, again plugging in the values, the x, the average, the standard deviation, we get 1.5. And so we can see that the woman's height is 1.5 standard deviations above the mean, which is the average height for women. So in this case, we can see that the woman is taller relative to the population of women's heights. So again, the z-score gives us some relativity for a point about how close it is to the mean, above or below the mean, and where it sits in the data. Sometimes we're given a z-score and need to find the value that has that z-score. And remember that the z-score, we have the calculation for the z-score, which is x minus the average, the data point minus mu, divided by sigma. If we rewrite that formula, solving for x, we get this version of it. So if we want to know a given z-score for a data point, or if we want to know which point has that z-score, we can calculate that data value right here. So in a population with mean mu and standard deviation sigma, the x value with a given z-score is x equals mu plus z sigma. So again, we might say, okay, what data value is 1 standard deviation, or a z-score of +1? And then we would use this form. Go ahead and hit pause and see if you can solve this. Data from the National Health and Examination Survey estimate that the mean total cholesterol level in milligrams per deciliter in the adult population to be mu equals 200 with a standard deviation of 44. What is the cholesterol level of a person with a z-score of 1.5? This is simply a plug and play. So go again, if you haven't tried it already, hit pause, solve it, and then come back. So again, the cholesterol level for a person with a z-score of 1.5 is 1.5 standard deviations above the mean. So here we put in 200. This is our average plus our z-score of 1.5 times the standard deviation, and we get 266. Since the z-score is the number of standard deviations from the mean, we can easily interpret it for bell-shaped populations using the empirical rule. The diagram you see at the bottom is really based on that empirical rule that 68% of the data is within one standard deviation plus 1 or minus 1. 95% of the data is between plus 2, z-score positive 2, and minus 2 standard deviations, plus or minus 2 standard deviations. And then 99.7, or almost all, is plus or minus 3. And so you can see the z-scores. So really the z-scores really range from about -3 to +3, slightly more. Again, here's a good, just a quick check for you. Hit pause and see if you can answer these 3 questions. I hope you're taking advantage of the opportunity within the video to actually check your understanding, to check your notes. Everything you do on your own is reinforcing your recollection of the formulas, etc. Instead of being a passive learner, you want to be an active learner, and that's why I keep these in there and really encourage you to stop, pause, and try the exercises. We've already looked at how to compute the mean and the median of a data set as measures of center. Sometimes it's useful to compute other measures of position or specific measures of position that are not the center to get a more detailed description of the data. Quartiles divide a data into 4 approximately equal pieces of data. That means there's the same amount of data points in each quartile. The first quartile, denoted Q1, separates the lowest 25% from the highest 75%. The second quartile, Q2, separates the lowest 50% from the highest 50%. Notice this is the median value. Half of the data points are above, half of the data points are below. That is the definition of median. So quartile 2 is the median. And then the third quartile, Q3, separates the lowest 75% of the data from the highest 25% of the data. These are actually quite simple to compute. We arrange the data in increasing order. We find the number of data points we have. So this is n is the number of values in the data set. For the second quarter, we simply look at the mean, the median, not the mean. We simply compute the median, right? This is the middle value. For the first quarter, we take L equals the first quartile will be 0.25n. This is the data. This is the position for that data point. And for the third quartile, we use L equals 0.75n, and this gives us the position of the third quartile data point. Now, similarly with the mean, if the L is a whole number, the quartile is the average of the number in the L position and the number in the L plus 1. So it's a little bit kind of reverse from median, if you might think. If L is not a whole number, we just round it up to the next whole number, and the quartile is the number in the position corresponding to the rounded up value. So if we calculated this and we got L equals 20, then we would take the data point in 20 plus the data point in 21 and take its average, and that would be the value of the first quartile data point. If L is not a whole number, let's say it was 13.5, then we would simply round up to 14 and we would look at the data in position 14. Again, remember we've already put this in increasing order. So let's try this. See if you can find all three quartiles, quartile 1, quartile 2, and quartile 3. Again, the data's in order. You have 45 data points. See if you can compute those quartiles. If you haven't done so already, hit pause. So for the second quartile, the median is the middle data point. Since we have 45 data points, we have 22 values before, 22 values after, and so the median is in position 23. The data in that position 23 is 3.12. For the first quartile, we're going to take the 45 data points times 0.25. Here we get 11.25. It is not a whole number, so we round up to 12, and then we go to the position, the 12th data point, which in this case is 0.92. For the third quartile, we're going to use the formula L equals 0.75 times 45, and we get 33.75. Again, it's not a whole number, so we just round up to 34, and we go to the 34th position, 15, 30, 1, 2, 3, 4, and the data in that position is 4.89. Here you can see the quartiles, and I like this diagram because a lot of times we think that it would look like 4 equal pieces, but it really depends upon how the data is spread out. And so you can see here that most of the data, the upper end of the data is spread over a much more larger, it has a much more larger spread, the top 25% of the data. The bottom 25% has the smallest spread. It's in the smallest area. So these aren't dividing it like equally by spread, it's the number of data points. Okay, where is the data in the graphs? So your technology does this automatically for you if you have those input values, etc. And again, your book 3.3 has a great section on this measures of position and how to use Minitab, how to use your calculator, how to etc. This is a close-up of the TI-84, and you can see you've got the quartile 1, you've got the median, which is quartile 2 in between them, and of course the third quartile. And again, this is all directly from, here you see it with Excel. Quartiles describe the shape of a distribution by dividing the data points into fourths, as we just saw. Sometimes it's useful to divide a data set into a greater number of pieces for a more detailed description. And percentiles is something that we use very much. Most people understand percentiles. 100% is everything, 50% off is half the price, etc. So using percentiles is kind of a well-known kind of measurement for the majority of the population, even those who might think of themselves as mathematically challenged. Percentiles divide the data set into hundredths. For a number p, the percentile between 1 and 99, that pth percentile, so if p equals 1, it's the first percentile, separates the lowest p% of the data from the highest 100 minus p. Now this is a confusing explanation or wording to explain this, but most of you understand this because standardized testings generally use this. If you took the star or something in school and you scored in the 90th percentile, that means 90% of the people taking it scored lower than you and 10% scored higher than you. And so that's all this is saying, that if I'm in the 90th percent, if p equals 90, 90% scored lower than me, 10% scored higher than me. So here's how we compute percentiles. Again, you arrange the data in increasing order. N is the number of values or data points we collected in the data set, and for whatever percentiles we're looking for, It's P over 100 times N. And again, this will give us the position of the data point, like the 50th data point, the 30th data point, the 38th, etc. And of course, we follow the same thing. If it's a whole number, we average L and L plus 1 position data values. If it's not a whole number, then we simply round it up. Okay, so let's try it again. Here we have the same data as before, 45 data points. We want to calculate the 60th percentile. Okay. The data is increasing order already. There are 45 values. We want to calculate the data position for the 60th percentile. Remember, this is simply 60, the percentile over 100, times the number of data values, and we get 27. So we simply go to the 27th position. Actually, since this is a whole number, I missed that completely. Since this is a whole number, 27, we're going to go to the 27th and the 28th, L plus 1's position, and we're going to take an average of these two numbers. Okay, we would do the same thing for quartiles if when we calculated the average or the position, it was a whole number, not a decimal. And here we take the average, we get 3.645, and so the 60th percentile is a amount of rain of 3.645 inches. So 60% of the rain, annual rainfall during the month of February, 60% of rain is below 3.645, and 40% of the rains in February are above 3.645 inches. Suppose we are given a value from a data set in which to compute the percentile corresponding to the value. So again, here's how we do it. We arrange the data in order. We let X be the data value whose percentile is to be computed, and we use the following formula. So we take the number of data values less than X. So if the value we pick is in the 20th position, there are 19 values less than X, plus 0.5, and then we divide it by the total number of values in the data set and multiply that times 100 to give us the percentile. Always round to the nearest whole number, and this is the percentile corresponding to the value X. Again, the percentile for a specific value is figure out what position your value is in. Okay, say it's 27, then there's 26 values less than that. That's what we put here, the number of values less than that data point. Add 0.5, divide by the total number of values, your lowercase or uppercase n, and then times it by 100. Again, let's try a problem. Here we're looking for the percentile that corresponds to 1.9 inches. Okay, the data is in order, so you can figure this out. Hit pause and try this problem. So I remember that there's 15 datas in each row, so 15, 16, 17, 18. 1.90 is in position 18, so that means there's 17 values below this value of X. And there's 45 values in total, so I plug in those numbers. 17 plus 0.05 divided by 45 and times 100, I get 38.9. I then round it to 39, so the value 1.90 corresponds to the 39th percentile. That is that there's 39% of the rains in February are below 1.9 inches, and 61% of the rain in February is above 1.9 inches. Again, here's some problems. I'm not going to go through these on video. Just hit pause, try these problems, and then hit play, and you'll see the answers. Similarly here, try these. Again, hit pause, try to solve these, and then check your answers. The five number summary of a data set is a very common thing we use in statistics, and it just lists out these numbers to give us different ideas of the data. Okay, so it includes the median, the first quartile, the third quartile, and then it also includes the smallest value and the largest value. Typically, these are arranged in order. So you have the lowest value, the first quartile value, the median value, the third quartile, and the maximum. Provide this, but here we can go back and look what we did before. Okay, we already computed the quartiles in this exercise. I'm not going to go through that. You can go back and look at that. The only thing we're missing here is the absolute minimum value, or the smallest value, which is the first value, and of course the maximum value, or the largest value, which is the last value. We then just simply put them in order, and this is the five number summary. Again, all the technologies do this. You can see it with Minitab. You see the five values circled. You see it with your TI-84, etc. Okay. An outlier is a value that is considerably larger or considerably smaller than most of the values in a data set. Sometimes outliers result from errors, just like, for example, I'm typing things in, and one of the most common is a misplaced decimal point that can make a number much larger or much smaller. Some outliers, however, are correct values. They just represent that there's a different opinion or a different measurement for a small population or a small number of people responding or being observed. There just sometimes are extreme values. The temperature in a downtown location is measured for 8 consecutive days during the summer. Here are the readings in Fahrenheit. Do you see any reading that stands out as an outlier? It's either much larger or much smaller. Hopefully you can see something pretty quickly. The outlier 8.45. Now this is the temperature in summer, and you can see that this is really different. What is likely that is happening here? It's likely that this is an error, because we can see that all the rest of the temperatures are right in the 80s or 90s or close to it. So it's likely that this was just typed in wrong and it should be 84.5. What we would do here is go back and look at that data point and then correct it in our data set. Here we have another example. The table represents the population of the 5 largest cities in the United States. Here we have New York, LA, Chicago, Houston, and Phoenix. Again, looking for a number that is much greater than or much less than. Well, the very first value of the population of New York, we can see is 8.6 million. And you might think by looking at the data, because if these are the 5 largest cities, that's wrong, but it's actually not wrong. That is the population. It's just much higher than most other cities. Now, again, you might, if you had that doubt, like, oh, I wonder if this is correct, you would go back and look at your original data collection to see if you can validate it or if you need to correct it. So, often a way that we want to talk about outliers and have a common reference point for outliers is using something called the interquartile range. So that all statisticians are using the same kind of mathematical calculation to determine what makes an outlier. So the interquartile range is a really simple value. It is simply a value of taking the quartile 3 and minus quartile 1, okay? Subtracting the first quartile from the third quartile. That's all it is, and this gives you a numerical value. So we find the first quartile, we find the third quartile, we find the interquartile range, Q3 minus Q1. And then we create boundaries. What this means is we use this value that we calculate, and we say the lower boundary is quartile 1 minus 1.5, this quartile range, and then we have a lower boundary, and if an outlier is below this value, if a data point is below this value, this boundary we create, then we say that it's an outlier. And we do the same thing for quartile 3. We add 1.5 times the interquartile range. So we have an upper boundary to the right of the graph of all the data. And if a data value is greater than this, then we call that an outlier. So any data value that is less than the lower boundary or greater than the higher boundary is considered an outlier. And this just gives us, again, a numerical method so that we're quantifying outliers the same way. The following table represents the number of students absent in a middle school for each day. Identify any outliers. Again, try this. You should be able to calculate the quartile 1, the quartile 3, and then the boundaries, the upper and lower boundary. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 22 data points. Okay. So 22 times 0.25 will give us quartile 1. 22 times 0.75 will give us quartile 3. However, here I've gone ahead and used the data. So you have it there. All right. So what I'm going to do now is calculate my interquartile range, which is quartile 3 minus quartile 1, and we get 14. The upper boundary is going to be quartile 1, which is 45 minus 14 times 1.5, and I get the lowest value is 24. I'm going to do the same thing with the upper boundary. I'm going to take quartile 3 plus 1.5 times the interquartile range, and I get 80. So what I'm doing now is I'm looking for any data that is below 24. Don't see any, so I don't see any low outliers. And then I'm looking for any data, I've got 100, that is above 80. Okay, so I have one data point that is above 80. And so again, I have no lower boundaries or low small outliers, but I do have an upper outlier or a large outlier. Again, we have some problems here for you to look at and try. I'm going to just go through these. I'm not going to do it, but again, you're going to do better in the class if you hit pause, you try these problems, and see if you get them in here, and then go to the homework. The last thing we're going to talk about, I believe, is something called a box plot. A box plot is kind of a visual graph that represents the 5-number summary along with some additional information about the data set. Okay. What we're looking at here is a modified box plot. I'm going to walk through this. Notice here the box in the middle is created by the quartile 1, the quartile 3, and the median. Then these are the lower, we call these whiskers. These are the lower boundary. So from quartile 1 to the lower outlier boundary, from quartile 3 to the upper outlier boundary. And then we draw in any outliers we mark with X's, whether they're large outliers or small outliers. So let's go through. Let's go back to the number of students absent in middle school for each school day in January. Okay. So remember, here we have the data. The box, we use the quartile 1, the median, and the quartile 3. And so what we're going to do here is we're going to draw vertical lines at 45, 51, and 59. And then we draw the vertical lines, and then we make this into a rectangle. The next thing we're going to do is we're going to draw the whiskers, and that is subtracting 14 from 45, adding, I lied there, 45 minus 1.5 times the interquartile range, and quartile 3 plus 1.5 times the interquartile range. Not adding or subtracting this number. Remember, we multiply by 1.5. So our lower whisker is going to go down to 24. Our upper whisker is going to go all the way up to 80. We can see that this table does not go all the way down, so we're going to have to adjust the table. This is not a very good drawing that matches with this data. And then the last thing is to put the outlier there. So this is really quite confusing, since the data should go down to 1.24, right? So I just pause for a minute and redo the calculation. The calculations are right. This is just really a poor graphing. I talked about mistakes we make in graphing that lead people astray, and this is a big one, because notice how the lower boundary should go down to 24 and it stops at 40, and even the upper boundary doesn't go to 80. So this gives you kind of a relative idea, but this is a really poor statistically drawn graph, because it doesn't even include the boundaries like we should see here. Very disappointed in this. Anyway, so hopefully you get the idea, and you also get a good example of what not to do. Make sure that when you're drawing a box plot, you can see all the values, and this should go down well below 20, or to at least 20. Again, all your technology draws box plots, and at the end of this section of the chapter. So one of the cool things is, if you look at the whiskers, okay, if the median is closer to the first quartile, okay, so you see, the box, the rectangle, the box isn't equally divided. The median is more to the left. This makes the upper whisker typically longer, and so the data is skewed to the right. If the whisker is longer to the right, it's skewed to the right. If similarly, if the median is closer to the right and the whisker then on the left is longer, then it's skewed to the left. And when the median is approximately in the middle of the box and the whiskers are approximately the same, then the box plot tells you that you have data that is approximately symmetric. So the box plot quickly tells us if we have a skewed right, skewed left, or a relatively symmetric data point. And so that's one of the biggest reasons we use the box plot, to quickly tell if we have symmetric data. Again, this is what you should know from this section. And take a quick note, make sure you understand how to do all these things. And that's the end of our lecture.